Hi and welcome to this next video in our probability series where we will be looking at tree diagrams and the concept of independent events. We can use tree diagrams to illustrate more than one event taking place. These events could be flipping a coin, then rolling a dice, or flipping more than one coin or rolling more than one dice, or any repeated event or events. Let's consider the flipping of two coins. The first two branches of the tree diagram offer the two options for the first flip, heads or tails. Then, if the first flip is heads, we track along this branch to find the options for the second flip, which follow here, again heads or tails. Or if the first flip is tails, then we track along this branch of the first flip, and then the second flip options follow here this time. We now have our tree diagram, which illustrates nicely for us that when flipping two coins, altogether we have four possible outcomes: two heads, heads then tails, tails then heads, or two tails. Now, if we talk probability, because there are four possible outcomes in total, the chances of getting any one of the outcomes is 1 in 4, and so the probability of getting two heads or two tails is a quarter, and the probability of getting heads then tails or tails then heads is also a quarter if the order matters. But if we were to consider getting one heads and one tails in any order, then we can see here that 2 out of the 4 outcomes fit these conditions. And so the probability for this would be 2 over 4, which we can simplify to a half. To find the probability of events happening, we find the product of their probabilities along a path, and we call this the product rule. In other words, if you have 2 or more events, say A, B, and C, the probability of all events happening is simply all the probabilities multiplied together. So if we consider the example of getting 2 heads when flipping 2 coins, the probability of it landing on heads each time is a half, and so by tracking this path, we can see the product of a half and a half is then a quarter. And if you remember from the previous slide, the outcome of 2 heads when we were focused on the outcomes was 1 of the 4 possible outcomes. And so these two methods correlate, which is great news, because when the scenario gets more complex, we know we can rely on the product rule. What about when there is more than one path to consider? Well, for this example, where it is asking for the probability of landing heads or tails in any order, for each path we use the product rule, and then we add the products of the probabilities from each path to get the probability of all possible outcomes. Again, you may recall from earlier when we were looking at the outcomes for heads and tails in any order, we found that there were 2 out of the 4 possible outcomes that met this requirement. And so the answer of a half correlates with this rule here, which also results in the answer of a half. Now we come to the concept of independent events. These are events where the outcome of the one event does not influence the outcome of the other. In other words, the probability of A and B occurring is equal to the product of the probability of A and the probability of B. So if we go back to the example of landing 2 heads, the flip of the one coin does not influence the flip of the other coin. And if we look at the probabilities, we can see here using the product rule along this path that the probability of landing 2 heads is a half times a half, which gives you a quarter. But we also know from looking at the 4 possible outcomes that to get 2 heads, there was a 1 in 4 chance. And so because these both give a quarter, we can confirm that for independent events, the probability of landing heads and heads is equal to the product of the individual probabilities. If we look at the theory for a moment and remember this equation that is true for any 2 events, then we can see that for independent events, the following equation is true because for independent events, the probability of A and B is equal to the probability of A times the probability of B. Let's dive into an example now. This example is about 5 orange Smarties and 3 blue Smarties that are left behind in a box. The question is asking us to consider 3 scenarios when selecting 2 Smarties from the box for 2 cases. The first case, if the Smartie selected is replaced, and the second, if the Smartie selected is not replaced. Maybe pause the video for a moment to read the question in full. A tree diagram is a great option to use in answering this type of question. For case 1, where the first Smartie selected is replaced, there are 8 Smarties altogether, 5 orange and 3 blue, and so the probability of selecting an orange Smartie is 5/8 and a blue is 3/8. And then for the selection of the second Smartie, these probabilities are the same, and so we place them each on their branch. Note here that these probabilities in each case add up to 1. The probability of selecting 2 blue Smarties then would be this path, and so using the product rule, 3/8 times 3/8 is 9/64. Then for B, the probability of selecting 1 orange and 1 blue Smartie in any order, because the order doesn't matter, there are 2 paths we can follow to get this outcome, and we use the product rule along each, 5/8 times 3/8 and 3/8 times 5/8, and then we add these probabilities. And this then simplifies to 15/32. And then for C, the probability of selecting at least 1 orange Smartie, in other words, the options can include 1 or 2 orange Smarties. There are 2 ways to tackle this concept. The first way shown here is to consider all the outcomes, including 1 or 2 orange Smarties, and so in each case we find the probability and then add them together. Alternatively, you can find the probability of not getting an orange Smartie and then use complementary events in order to calculate the probability of selecting at least 1 orange Smartie. The probability in each of these works out to 55/64. Now for case 2, where the first Smartie selected is not replaced, you will notice the probabilities on the second set of branches of the tree diagram need to be different. Overall, there is 1 fewer Smartie in total, so only 7 Smarties left in the box, and depending along which branch you go, the number of blue or orange Smarties must be adapted where necessary. So where an orange Smartie has been selected and not replaced, the total number of orange Smarties becomes 4, otherwise it remains 5. And where a blue Smartie has been selected, the number of blue Smarties then becomes 2, otherwise it remains 3. Note here that even though these probabilities needed to change, they still in each case add up to 1. Let's take a moment to consider the concept of independent events here. We can immediately see that the selection of the second Smartie is influenced by the selection of the first Smartie because it is not replaced. We can therefore say that the 2 selections in this case are not independent. Whereas if we think back to case 1 where the first Smartie selected was replaced, that was an example of independent events. Remember, for independent events, the outcome of one event does not influence the outcome of the other. With tree diagrams, it is clear to see when events are independent or not. For other situations where it's not so obvious, we may need to prove events independent using the theory we just spoke through. Okay, so let's have a look at these solutions now. The probability of selecting 2 blue Smarties when the first Smartie is not replaced is 3/8 times 2/7, which simplifies to 3/28. And then for B, the probability of selecting 1 orange and 1 blue Smartie in any order, the 2 paths are 5/8 times 3/7 and 3/8 times 5/7, and then we add these together, and this simplifies to 15/28. The third part of this question, for case 2, can also be done in 2 ways, either by considering 1 or 2 orange Smarties in the outcomes, or by considering no orange Smarties in the outcome and then finding the complement. So here we need to find the probability of all three of these paths and then add them together. And here we need to find the probability of this one path and then find the complement by going 1 minus this probability. In both cases, the answer is 25/28. It feels like a good moment to capture a quick summary of the theory we have covered so far. It may be a nice idea for you to make notes somewhere for yourselves as well. So the rule that is true for any two events. Then the rule for mutually exclusive events, P of A and B equals 0. And we can see how this impacts the general rule, where this is just plus 0 on the end. Then the rule of independent events, P of A and B equals P of A times P of B. And we can see how this impacts the general rule. And lastly, the rule for complementary events, the probability of one event is 1 minus the probability of the other. You may want to pause the video here for a moment if you would like to make some notes.
Check out the video description below for practice questions from our study guides. If you found this video useful, give it a like and subscribe to our channel so you don't miss any new episodes. Follow us on Instagram or Facebook to stay on top of the latest TAS news and launches. So that's it for now from the Answer Series, your key to exam success.